right, so we're on Unit 9 still. This is our last set of notes before the test Tuesday. This is over inverses for cubic and cube root functions. Okay, so we're going to start with this warm-up, going over what was on the quiz yesterday, the notes we took beginning of this week on Monday and Tuesday. So go ahead and take a couple minutes to try these warm-up problems. Okay, and then we will check to make sure you've got those down. Okay, so these are similar to what was just on the quiz yesterday. If you're watching this as a video, you can just pause and try those and then fast forward or unpause and fast forward to check them. All right, how y'all feel about those so far? Think you've got at least one of them? Okay. All right, I'm gonna go ahead and unfreeze the screen so y'all can check. If you hadn't finished them both, that's all right. Get copied down as we go over them. So in number 1, this is very similar to one of the quiz questions yesterday. And I think the people who were messing up on this one, the ones that were doing it algebraically and messing up, it's because this constant threw them off because it's in front on the outside instead of after on the outside. Okay, it does not matter where your constant is, it should still be the first thing that moves. Okay, so instead of having +5 back here, there's a +5 at the front. Okay, but it still gets moved by opposite operation. So this 5 is subtracted over, that negative, okay, or that minus stays there in front of the parentheses. It's an understood -1 as a coefficient. So then I divide out the -1, which leaves me with the x plus 3 to the 1/3 power equals 3, +3. Then I'm to the point where I've isolated my expression that's raised to the power. So now I'm ready to try and get rid of the power. And to do that, we talked about in our notes on Tuesday, if it's a 1/3 power, okay, you're going to cube it because the 1/3 and the 3, when you multiply a power to a power, that comes out to 1. Okay, so then we cube both sides to keep it balanced. We end up with x plus 3 equals 27. And then we've got the constant that was inside the function that needs to be moved over by subtraction, and you end up with 24. And I did check these. The 24 works. If you take 24 and you plug it back in, the left side does indeed equal 2. Okay? I think 2 was a little more straightforward. I feel like this one was easier for most people. So you subtract the constant over, divide the coefficient over, and then you're ready to get rid of the cube. So the opposite operation is to take the cube root. So we cube root both sides, leaving us with -3. And again, I did check this. If I were to plug in a -3, this would equal 0. Now, if you are one of the people who is choosing to do these graphically, that's fine. Number 2 was nice and set equal to 0 already. So you would just graph that and look for the x-intercept. Okay, number 1 was not set equal to 0. So you could either do y equals the left side and y equals the right side separately and find the point where they intersect, what the x is. Or you could move that 2 over to the left by subtracting so that it is set equal to 0. And then you could graph it and look for the x-intercept. Y'all feel okay about what we've been doing for the most part of this week? Okay. What we're going to look at today are inverse relationships. Okay. This is not brand new. Okay. We have talked about what inverses are. You should recognize a lot of what we're about to fill in here. Okay. It says that blank relations interchange the x values inputs and y values outputs. Well, that's inverse relations. That's what we're talking about today. So inverse relations, you switch x and y. So x and y switch. Whether you're looking at a graph and you just switch all the x's and y's to get your new points for the new inverse function, or algebraically, if you have an equation, you switch the x and y. Okay, that's what we're gonna be practicing today with cube and cube root functions. A relation and its inverse relation reflect over the line what? Who remembers graphically what line inverses reflect across? Does anybody recall? If I have the x and y axis here, what is that line? I'll draw it. It's this line through the origin with a slope of 1. It's this one that's at a 45-degree angle here with the x-axis. With each axis, it's a 45-degree angle. They reflect across this line. What is the equation of that line? What type of function is that line? Linear. It's a line. It's linear. Okay. Anybody? It's the linear parent function. What is that? Nobody remembers the linear parent function? It's got a slope of 1 and a y-intercept of 0. It's just y equals x. That's it. Thank you. Okay, slope of 1 and then y-intercept of 0. So when you think about mx plus b, m is an understood 1 and b is 0, so you don't even write it. So if you have two functions that are inverses of each other and you were to look at them graphed on the same grid, they would be a reflection of each other across that line. So I'm going to go ahead in Desmos and get us ready to look at some. And I'm just going to have the line y equals x. And remember, if you hold down this little circle over here, you get these options. And I made mine dashed and black. Okay. And you can do the same thing. Just to have that in here, when I graph two functions, I want to see that visual of that dashed line so I can tell, are those reflections of each other across that line? Okay, so I'm just going to have that in there and ready. Now, inverse functions reverse each other. Okay, an inverse function is an inverse relation that is also a function. Relation is just another term a function is a relation, but not all relations are functions. If you remember, back in Algebra 1, when you were asked to determine if the relation is a function or not, it had to pass the vertical line test. Do y'all remember that? So that's what we mean when we're saying relation and function. Okay, so relations can still have inverses. Okay, functions can have inverses, but sometimes the inverse may not be a function because it would fail the vertical line test. So that's why we're referring to them as relations here. Okay, but it can be a function. A function just would mean it would pass the vertical line test when we graph it. All right, the process of solving to find an inverse is one, if it's given in function notation, your equation is written as f of x equals, we're going to replace y for f of x. And then we're going to switch the x and y in the equation. And then we're going to solve for y. And then we're going to rewrite it again back in function notation because that's what it started with. Okay. You should always use the same format that the equation's given in to give your answers in. Okay. So the inverse of f of x is written as, I know you've seen this before because we've talked about it before. It's written with that little -1. Kind of looks like an exponent or a power. It looks like this. F. And then it's got the little -1 there. And then you've got your x still in parentheses. Okay. Everybody good with that? Y'all remember that? Okay. So then a lot of people get mixed up with how they read that. So I'm going to put it in words here. So this is read f of x. So we're going to read this as f inverse of x. So this step 4, where it says to rewrite in function notation, that's this right here. So our final answer is going to be written f inverse of x equals, and then whatever the equation is for the expression. Good? All right, we're going to start with the parent functions and make sure that we understand the cube and cube root inverses. Before we get into transformations, we're just going to start with parent functions. So the original function is f of x equals x cubed. So if I want to find the inverse, I'm first going to rewrite y in place of f of x. So I write it as y equals x cubed. Then I switch the x and y, so it becomes x equals y cubed. Now I'm ready to solve for y. So in the process of solving, what am I going to do to get rid of that cube on the y? What's the opposite of cube? Cube root. This is what we've been doing all week, y'all. Cube root to get rid of the cube. And what you do to one side, you do to the other, right? So I take that to get rid of the cube over there. So then I've got the cube root of x equals y. But the thing is, it doesn't equal y, it equals the inverse. So I'm going to put that little -1 there on the y to indicate this is the inverse now. But they want us to put it back in function notation. So instead of y with the little -1, inverse of y, I'm going to say f inverse of x equals cube root of x. Notice I switched the left and the right. You're allowed to do that. It doesn't matter which is on the left or the right, as long as you move it in its entirety. Now they also ask us to graph the function and its inverse. Okay, so I'm going to graph the original function. We'll do it in green. So the original function is x cubed. We've talked about the parent cube function goes through 0, 0, 1, 1, -1, -1, and 2, 8, because 2 cubed is 8, and -2, -8. Everybody recognizes this, right? This is what we did last week and have continued practicing this week in our ALEKS, is graphing cubics. So that's the parent function that we start with. I'm going to call that's what we said is f of x. Okay, now the inverse do that one in pink. The inverse is the cube root of x. Well, the cube root of 0 is 0. The cube root of 1 is 1. Cube root of -1 is -1. Remember those first 3 points there were exactly the same? Do y'all recall that? Last week? But instead of going to 2, 8, what did we do? We went to 8, 2. Because the cube root of 8 is 2. So 8 becomes the input, 2 becomes the output. Notice the x and y switched. Okay, so same thing over here. Instead of going to -2, -8, we're going to go to -8, -2. Because the x and y switched. So this is the inverse. We have the original and the inverse. Now, for funsies, I'm going to put that y equals x there so you can have a good visual. So there's that line, y equals x. Does it appear, if I were to fold this along that dashed line, that all of the green graph would match up with all of the pink graph? If I folded it on the dashed line, wouldn't this 2, 8 and this 8, 2 match up if I was folding it on this dashed line? These would match, they would, because they're inverses. All of their coordinates, the x and the y, are switched. Okay, and you can look at this in Desmos. If you're not great at graphing by hand, that's okay. Let's check it out here. We have x cubed. I think that's the one I did in green. And then we have the cube root of x. Look at that. That looks like what we graphed, doesn't it? I mean, if you zoom in, theirs is a lot more accurate than our hand graph, because when it came through here, it had that point of inflection there. So you see kind of little loops there. We can't zoom in because it's between 0, 0 and -1, -1. That's so tiny on our graph. Like, that's like this little square right here. So I didn't really draw those loops don't show up that great here, but it's the same graph. So you'll feel okay about that? You would definitely, if you folded that over that line. Everybody good? Okay. Now, example 1b says, okay, now what if we start with the cube root and want to find the inverse? Well, using logic, you probably know what it's going to come out to be, I would think, but let's show it. Let's show if we start with the cube root, I'm going to replace f of x with y. I'm going to switch X and Y. And then I'm going to solve for Y. How am I going to solve for Y? How do I get rid of a cube root? What's the opposite operation? Come on, guys. We've been doing this all week. When we're solving, how do we get rid of a cube root? We cube it. What you do to one side, you do to the other. So to get rid of that, I end up with x cubed equals y. But that's my inverse of y, right? So then I rewrite it in function notation. So f inverse of x, and then this is equal to x cubed. I am not going to make you graph that again because that's going to be the exact same graph we just put up there. We're going to have the cube and the cube root. So you can see whether you start with the cube and find the inverse or start with the cube root and find the inverse. You end up with the other. Do y'all see that? So cube and cube root are inverses of each other. Now, I already showed you graphically how you can visualize inverses, how they are a reflection of each other over that line. Algebraically, there is a way to check inverses as well. I don't think as many people are going to use it because I think, not that it's too hard, but people just prefer graphing, I think. It is easier. But I do want to just show you real quick at the bottom here. I know there's not a lot of space, but if you take your original function and you replace x with the inverse function, so I'm plugging the inverse into the original, or I can have the inverse and plug in the original. It doesn't matter which way you do it, but if you plug an inverse function into its inverse, or an inverse into the original, either way, they should come out equivalent to each other. They should come out to equal just x. All of the operations should reverse each other. That's what we said up here when we said the inverse functions reverse each other. Everything's going to end up eliminating and you're just going to be left with x. Okay, so with the parent functions as an example, if I have the cubic function and instead of x, I plug in the inverse. The inverse is the cube root, isn't it? Do y'all agree? So I am taking I'm replacing x with the cube root of x. Okay, see, I'm plugging it into the other function. What happens there? What does cubing a cube root do? What does cubing a cube root do? Yeah, that's how we eliminate it, right? They're opposite operations. So what am I left with there? Just x. Hey, that's what I was supposed to be left with if they were inverses. Everything was supposed to reverse each other, eliminate, and just be left with x. It works the other way as well. Instead of starting with x cubed, if I start with the cube root of x and I replace x with the inverse, we said the inverse was x cubed. I end up doing the same thing. My inverse, cube and cube root, eliminate each other, and I'm left with just x. So do you see what I'm saying there? If you input a function into its inverse or vice versa, it should always come out to just x. Everything should end up eliminating down to the x. Okay, let's flip over and let's try some that have transformations. These are not the parent functions anymore. We've got to do some actual solving here. So first, replace f of x with y. That's step 1. What was step 2? What's the definition of an inverse? We switch x and y. Okay, so replace f of x with y, switch x and y, then what? Solve for y. We're going to try and get this in y equals again. Okay, so I need to isolate that y. To start, we just have been talking all week about solving cubes and cube roots. We have to isolate the expression raised to the power. So what needs to be moved away? The 7. So I'm going to subtract 7. Okay, now what we've been doing earlier in the week, this was a number over here. And so we were combining these, but now it's a variable. So we just leave it as an expression, x minus 7. So now I have isolated my expression that's raised to the power. Now, how am I going to get rid of that power? How am I going to get rid of that power of 3? Cube root. The opposite of cube is cube root. That's the opposite operation. And what you do to one side, you do to the other. So it gets rid of it over here. And I've got the cube root of x minus 7 equals y minus 2. Almost got y alone. What do I have to do still? Add the 2 over. Now, here's where a lot of people might make a mistake. If you go over here and you write plus 2 right here, don't do this. But if you write it right there under the other number and you combine those, that's wrong. Why do you think that's wrong? Does anybody see a difference in that 7 and that 2 and why I should not be combining them? Where is that 7 located? It's under a radical, okay? That 7 is part of what we're taking the cube root of. So I cannot now, this 2 is not under a radical. It's just a normal 2. So I cannot combine those because that's not just a normal 7. Do y'all understand that? So to help me make sure I don't accidentally combine those, I'm going to put plus 2 off to the side here so they're not lined up and I don't accidentally add them together. Okay. So I've isolated now the y, and I've got a 2 being added to this cube root. So there's actually 2 ways you could write this. You could write the cube root of x minus 7, and then your plus 2. It could go at the end here, but notice it's not under the radical, or it could be written in front as 2 plus. Either way, that means the same thing. I think we tend to prefer to have our constants at the end. So I'm going to keep it in that format. But if you wrote 2 plus the cube root of x minus 7, that's not wrong. You need to know that those are equivalent to each other. Now, this is the inverse of y, right? That we just found. And our original was given in function notation. So we're going to go back and write this in function notation. So f inverse of x equals. So that's going to be the cube root of x minus 7. And then the plus 2 not under the radical. So the minus 7 is inside, the plus 2 is outside. Because remember, that makes a difference. If I were graphing this, this would be up 2 and right 7, right? Correct? Okay, so those are inverses. If you wanted to check, you could come up here and replace the x with this entire expression and see that it eliminates. Okay, so I'll do this for us. I'm not going to do this on all of them, but I'll do it to show you. So if I replace the x with this entire expression here, here's what happens. Got the cube root of x minus 7. Then I've got plus 2. And then that's all in place of x. So then I've still got minus 2. And that is all raised to the third power. And then a 7 is added on the outside. So if I were to do this, process order of operations being followed, the plus 2 and minus 2, that's 0. So that's gone. So then I've got the cube root of x minus 7 cubed. Well, what do the cube and cube root do with each other? Yeah, that eliminates. So then I've just got x minus 7 and then a plus 7. What happens with the minus 7 and plus 7? What's negative 7 plus 7? It's 0. So that's gone too, and I'm left with simply x. And so that proves to me, that's a way that I can check that worked. That is the inverse because it all eliminated down to just x. You do not have to check it algebraically every time, but I just want to show you that that's an option. Okay, it should always eliminate down to x when you do that composition of a function and its inverse. Okay, graphically, you could check this. So coming back to my Desmos, let me get rid of the parent functions here. I'm going to change this to the original function, which was x minus 2 cubed plus 7. And the inverse we came up with was the cube root of x minus 7. And then on the outside, plus 2. Okay, so the function and its inverse we came up with. Let's look at this on the graph. And remember, if you get your graph too zoomed out or zoomed in or something, you can always hit this home button and go back to center. Okay, and you can zoom out if you need to. Do those look like, if I fold it on the dashed line, that they're going to align? The red to the green? It does, right? Does everybody see that? If you are more of a visual person, with the graphs being easier for you, if this was a multiple choice question and it simply said, what's the inverse? And you had 4 answer choices that were equations written in this format, 1, you could eliminate answer choices that aren't the right type of function. If it started as a cube, what do you know the inverse must be? What is the inverse function of cubic? Cube root. So you could eliminate any answer choices that were not cube roots, and then you could check the cube root functions. You could just type in your original function, type in y equals x, type in your original function, and then type in answer choice A and see if they are reflections of each other. If they're not, erase A and type in answer choice B and check it. Do y'all understand that? You could work backward from your answer choices. So that's an option for multiple choice. Now, if it's not multiple choice, you cannot do that. You have to be able to find the inverse algebraically. Okay, but multiple choice, you do have more options on how to solve. Y'all feel okay about understanding what that graph should look like for a function and its inverse? Okay, let's try B. I'm not going to do any more checking like this. It's just going to take too much time. I want to make sure we get through our notes. If you want to practice checking, you're welcome to do that later. All right, so first I'm going to replace f of x with y. And then I'm going to switch x and y. And then I'm going to solve for y. Now remember, when you're solving a radical, a root, we want to isolate the root. Is there anything outside this radical being multiplied or added or subtracted that needs to move to the other side? No, it's already isolated, isn't it? There's nothing outside of it. Everything's under the radical. So we are ready to do what? How do I get rid of that radical? I'm going to cube both sides. So the cube is going to eliminate the cube root. Now I'm sorry. Y'all, nobody called me out. I've got two X's in here. I switched my Y to an X, but I didn't switch my X to a Y. That's supposed to be a Y in there. Let me fix it. There we go. Y'all call me out when I make little mistakes like that. Wasn't paying close enough attention. All right. So we replaced f of x with y, switched x and y, and now we're starting to solve. What's the next step in solving? I've gotten rid of the radical. I'm trying to solve for y. What needs to move now? That 9. So I'm going to subtract the 9 over. Now I've got a variable and a constant. I can't combine them. It just stays an expression. Okay, now what? I'm going to get rid of the coefficient, the 4. Opposite is to divide because those were being multiplied. Now here, you need to make sure you understand when you're dividing, everything on the other side has to get divided. So you can leave this as a singular denominator like this. Okay, so that's our inverse function. So written in function notation, that could be x cubed minus 9 over 4. But that's not the only way that it could be written. And you need to know the equivalent equations. You're dividing both the x cubed and the 9 by 4. So we could separate them and individually do that division. Okay, what is understood to be in front of this x cubed? What's the coefficient here? A 1. So if I were to separate this, this is 1 over 4 times x cubed. So 1/4 x cubed, and then minus 9/4. So that is equivalent. Both of those are correct. So if your answer choices are all in this format, great. But if you don't see your matching answer choice like this, and the answer choices have multiple fractions separated, you need to be able to separate those. If the fraction reduces, you will need to reduce it. 1/4 and 9/4 do not reduce. So there's no reducing to do there. Good? All right. All right, I'm going to take it up a notch. I'm going to combine step 1 and 2 just to save you some writing and save us some time. So I'm going to replace f of x with y and switch x and y all in one step. So I'm going to make this x and make this y, and that saves me a line of writing. Everybody okay with that? If that doesn't make sense to you, keep doing it in 2 steps. It's fine. Okay. Now I'm ready to solve for y. So I'm going to subtract the 6. I've got a variable and a constant, so it stays an expression. Now I've got to get rid of the coefficient. So I'm dividing by 8. I can leave it like this. And then I'm ready to take the cube root of both sides to get rid of the cube. So I end up with the cube root of x minus 6 over 8, or if I were to do what I did up there in the last one and separate those, I would have the cube root of, that would be a 1/8 x minus, and then 6/8 does reduce. What does 6/8 reduce to? 3/4. 6 and 8 can both be divided by 2, so we can reduce to 3/4. So both of those answers are correct and equivalent to each other. All right. Now, you know what? There's actually another option for how that one could be written that I just realized. When you're taking the root of a fraction, you're taking the root of the numerator and the denominator, and you can separate it that way. So I could think of this as the cube root of x minus 6 over the cube root of 8. And the only reason I see that to do that is because 8 is a perfect cube. What is the cube root of 8? 2. So I could write this as the cube root of x minus 6 all over 2. So technically that's equivalent as well. So any of those three formats are equal to each other. If you plugged all three of those in your calculator to look at them, it would all be the same graph. So when you're taking a root of a fraction, you're taking the root of the numerator and the denominator. So you could separate it that way. If your denominator was a perfect root, that would really be the only reason I would do that. All right, let's try D. All right, I'm going to switch x and y, replace f of x with y and switch x and y in one fell swoop here. So I've got this. My radical is isolated, nothing to move. So I'm ready to cube both sides. So the cube and cube root eliminate. Now to isolate my y, I've got to move the constant by opposite operation. What you do to one side, you do to the other. I cannot combine the variable and constant. It stays an expression. But I've isolated my y, so that's my inverse function here. So in function notation, f inverse of x would be x cubed plus 8. Now again, another reminder. If you start with a cube root, your inverse should be a cubic. If you start with a cubic, your inverse should be a cube root. On multiple choice questions, you're going to likely be able to eliminate some answer choices if some of them are the wrong type of function. All right, on E, switch x and y, replacing f of x with y. All right, my expression raised to the power is not isolated. I need to get rid of this coefficient of 1/2. How am I going to do that? What's the opposite of half? 2. I'm going to multiply by 2 to get that to eliminate. Okay, so multiply by 2. What you do to one side, you do to the other. So here, that's going to eliminate. Now I have isolated the expression raised to the power, and I'm ready to do my cube root. And what you do to one side, you do to the other. So here, that eliminates. I'm left with the cube root of 2x equals y minus 8. And now I need to move that 8. Now again, I'm not adding the 8 underneath. This 8 is not under the radical, only this that was already over here when I took the root radical. So this plus 8 is going to be on the outside. So it could be written in front as 8 plus or at the end as plus 8, but make sure it's not under the radical. So in function notation, that should look like this. All right, last one. Y'all are, your job is to try the exit ticket before you come back to class next time. Let me try and get one more done with y'all here. X equals the cube root of y plus 2 once I replace f of x with y and switch x and y. The cube root is already isolated, so I'm ready to cube both sides. And then I need to move my constant. So I end up with x cubed minus 2 as the inverse function. You just put it in function notation. All right. You're watching. So those of you in class, try the exit ticket before you come back to class Monday. Remember, Monday is our review day. You'll be working on your review. I'll have the key posted for you to check your work. If there's ones you're getting wrong or don't understand, you can then go into the video that I'll have, and you can fast forward to that problem and see me go through and work that problem. Okay, and your test is Tuesday. Y'all have a great 3-day weekend. You're watching this as a video. I'm going to go ahead and finish and do this exit ticket so they can go back and check this later. So if you're working it now, pause, try the exit ticket problems, and then unpause and see the work done. All right, so the first thing is to replace f of x with y, switch the x and y. And now we want to solve for y. So here we are going to move the constant 5. So I have x plus 5 equals y cubed. Now the term that is cubed is isolated, so we're ready to take the cube root of both sides. So that got our y by itself. So that's our inverse function. We want to put it in function notation, cube root of x plus 5. Okay, and on the second one, we start by replacing f of x with y, switching x and y. Now it is not isolated, so we've got to do some movement here. Subtract the 1. Now the cube root is isolated, so I'm ready to cube both sides. Notice here, I don't think we've had one like that yet. We go back and look. Here when we cubed, it was just an x. Same thing here when we cubed, it was just an x. Same thing here when we cubed, it was just an x. So here, it is not just x that we're cubing. We have an expression, x minus 1. The entire side has to be cubed. So you need to make sure that you put those parentheses around it. Okay, so that eliminates over here. And I've got x minus 1 cubed equals y minus 4. Okay, so then I've got to get rid of that constant that was underneath. Now that plus 4 is not going to be added to that minus 1. This is the same thing I was telling y'all up here, because that 7 is inside, this plus 2 is outside. Same thing. That minus 1 is inside, this plus 4 is outside. So I'm going to write it over here kind of to the side so you don't accidentally combine those. So it's x minus 1 cubed, and then you can write the plus 4 at the end, or you could have written 4 plus at the beginning. Those are equivalent. Both would be correct. You would need to recognize both for like a multiple choice question. It may be written with the 4 at the beginning being added or the end. You need to know that those are equivalent. That's what we end up with for the inverse here. And I will do one last check. I'll do it with number 1 here. When I say one last check, I mean checking algebraically that they are indeed inverses, and then I'll show you checking graphically again. Okay, so if I were to check algebraically, I'm plugging this inverse function in for x here. I'm going to make that substitution. So I end up with the root of x plus 5. That's in place of the x. That's all being cubed. And then I've got minus 5. Well, the cube root and the cube are opposite operations, so they eliminate and leave me with just the x plus 5. And then I've got that minus 5. And what do you know? Positive 5 and negative 5, that's 0. So I'm left with just x. So it does check out. Now, if I were checking graphically, we'll check number 2 graphically. So I've got the cube root of x minus 4 plus 1. And then I've got x minus 1 cubed plus 4. Let's look at that graph. That sure does look like an inverse. If I were to reflect across that line, these points would line up. And you can even check actual points. There's a point at 0, 3 on the green. So there should be a point at 3, 0. How about that? Because they're inverses, the x and y's are switched. Okay, this point here that was the y-intercept here should be the x-intercept of the green one. And you can see that. It just switched the x and the y. All right, so graphically checking, algebraically checking, okay, and algebraically solving. Remember, if you have multiple choice, you have options. You can work backward from your answer choices rather than doing just the algebraic steps. Okay, you do have to be able to do the algebraic steps because not everything is going to be multiple choice. So you do need to be able to do these. There's not an additional assignment over just inverses. This is practiced, though, in our review. Everybody has a copy of the review. You got those a few days ago, and you can continue working on those or start them if you haven't started it yet to be ready for our test Tuesday, and the review is due on Tuesday.